All right, in this video, we're gonna be discussing Series 5, since some of you weren't in class. And also I'm going to discuss the Koch Snowflake, because maybe you might see a similar problem on the test. So let's talk about the Koch Snowflake first. Okay, you start with an equilateral triangle of side S. Okay, so let's discuss the perimeter first. So the first perimeter is 3S. Then how much are you going to add to that? Well, if you remove a middle third of each side and replace it with another equilateral triangle like that, basically you gained 3S over 3's, right? Because you had to take out 1, but you added 2. So basically you gained 1 on each side. Okay? And then in the next iteration, you remove the middle third of each segment, like that. And you replace it with another equilateral triangle. So how many did you add there? Well, if you remember your quiz, you added 12, right? But each segment was only S over 9. And then in the next iteration, you added 48 S over 27. And basically, you just add up all of these numbers. Now, the key to doing the Koch Snowflake is starting from the second term. That's a geometric series. The entire series is not geometric. Starting from the second term it is. And that's the key to doing the perimeter and the area. So, if you look at here, what do I have to multiply this term by to get this? Answer is 4/3. What do I need to multiply that by to get that? So the common ratio is 4/3, and since it's greater than 1, the series will diverge to infinity. Now some of you on the quiz put like the absolute value of r is greater than 1, but that's incorrect, because what if r was negative 4/3? Then the series wouldn't diverge to infinity, it would just diverge. So a lot of you lost 2 points there. A lot of you also lost 2 points because you got confused between a sequence and a series. Because some of you were doing this, 3s plus, and then 4s plus. But see, you're not adding 4s, it's just that, see, this is the perimeter of the first triangle, this is the perimeter of the second figure, and so forth. And so, see, it's a sequence. So if you confuse the sequence and the series, then you also lost 2 points on that. Now let's discuss the area. So the area of the first equilateral triangle is √3/4 times the side squared. And then in the next iteration, you're adding 3 more equilateral triangles, √3/4, except the side is 1/3 of the previous one, so that would be S over 3. And then in the next iteration, you're adding 12 even smaller equilateral triangles, √3/4 times S squared, except that side is 1/3 smaller than the previous side, so that's S over 9. And then you're adding 48 √3/4 times the side squared, but each side is 1/3 of the previous one, so that's S over 27 plus dot dot dot. And again, starting from the second term, it's an infinite geometric series. And what is the common ratio here? What do I need to multiply this by to get that and that and that? Well, it's 4/9. So the sum of this series here is the first term, which is 3 times √3/4 times the side squared, all over 1 minus r. And then you add that to the first term, which doesn't follow the pattern. And you will get the answer. You should have gotten 2√3/5 times S squared. And that would be the area of the Koch Snowflake, and it converges. That's because the absolute value of r is less than 1, because r is 4/9. So make sure you know how to do this, because like I said, you might see something very similar on the test. Maybe the Koch square or something. Actually, I gave that on one test. I think I mentioned that in your class. Just be prepared for something like it. All right, so let's go over the problems here. Okay, so the first one, find the area under the curve y equal x squared from 0 to 2. So here we go. Here is the graph of y equal x squared. Now we already did 0 to 1, now we're just doing 0 to 2. So we need to compute this area right here. We want the exact area. We don't want an estimate, we want exact area. So what we do is we divide it into n equal parts, like that, okay? So the distance from 0 to 2 is 2. If you divide that into n equal parts, each one would be 2 over n. So this is 2 over n, 4 over n, 6 over n, all the way until you get to 2n over n. Do not write 2. You want it to be 2n over n. And we're going to use circumscribed rectangles, like this. It's just easier if you do. You can also do inscribed rectangles, but it's just easier if you do circumscribed, okay? So the area of the first rectangle, well, the base is 2 over n. In fact, every single base is 2 over n. So the first rectangle, the base is 2 over n, and the height would be the y-coordinate of that point. So if the x value is 2 over n, you plug it into the function to get the y value. So 2 over n squared. Second rectangle, the base is 2 over n, and the height would be the y-coordinate of that point, which is 4 over n squared. Third rectangle, the base is 2 over n. The height would be the y-coordinate of that point, which is 6 over n squared. And you keep on doing that until you hit the last rectangle. The base is also 2 over n, and the height would be the y-coordinate of that point, which is 2n over n squared. Now we need to simplify this. What can I factor out? Or for those of you who haven't figured it out yet, you factor out this, the first term. Okay? If I factor out that first term, what are you going to get? 8 over n cubed. Anyway, what's going to be left? You're going to end up with 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. And that's what you want because, hey, you somebody. We have a formula for that, right? What is that? N times n plus 1 times 2n plus 1 all over 6. So this is a formula for the sum of these n rectangles, but we don't want an estimate. We don't want like the sum of 100, 1,000, or even 1,000,000 rectangles. We want the exact area. So we're going to take the limit as the number of rectangles approaches infinity. And we know how to compute this limit, right? If the degree of the numerator is the same as the denominator, you look at the coefficients. So that would be 16 over 6, which of course reduces to 8 over 3. So this area is exactly 8 over 3. All right? So we can expect this problem on the test. Number 2. So what do we got here? 1 times 3 plus 3 times 5 times 5 times, well, plus 5 times 7 plus dot dot dot, all the way until you hit 999 times 1001, right? 9 times 1001. Okay, so we're going to have to use sigma notation on this. So n equals 1. Now, how many terms are there here? Are there 999 terms? Don't be ridiculous. Just think about it. There are 1,000 numbers from 1 to 1,000, and then these are just the odd ones, so there's 500, right? Okay, now how do you generate the numbers 1, 3, 5? 2n minus 1, arithmetic, right? How do you generate the numbers 3, 5, 7, and so forth? That would be 2n plus 1, another arithmetic. Okay, and then you multiply that. So what is that? 4n squared minus 1. Separate that into separate sigmas. N equal 1 to 500. 4n squared, but you can put the 4 on the outside, minus sigma n equal 1 to 500, 1. Okay, and then, hey, use somebody. That's 1 squared plus 2 squared plus 3 squared all the way to 500 squared. So we have a formula for that, right? 500. So basically n times n plus 1, which is 501, times 2n plus 1, which is 1001, all over 6, minus And this is 1 plus 1 plus 1 plus 1, 500 times. That's 500. Now on the quiz, you were given full credit for that. I'm not sure on the test because this one is not that hard to compute. Well, right off the bat, you can factor out a 500. Makes the number smaller. Anyway, I will leave the arithmetic to you. Okay, number 3. Write the first 3 terms of the power series of cosine squared x. Now, we already did sine squared x. Now we're doing cosine squared x. Now, there are several things you can do. One is take the power series. Oh, well, cosine squared means cosine times cosine, right? So you can take the power series of cosine x and multiply it by itself. So like this, 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus dot dot dot, multiplied by itself. Now I'm only expecting you to write 3 terms, so this is not that difficult. So you take the first term and distribute it. So take the 1, distribute. 1 minus x squared over 2 plus x to the 4 over 24 minus dot dot dot. Now you take the second term and distribute it, you get negative x squared over 2 plus x to the 4 over 4 minus dot dot dot. And then you take the third term and distribute it, x to the 4, what am I doing? X to the 4 over 24. How about line it up right, minus dot dot dot. See how, if I'm only expecting to write 3 terms, it's quite easy. Line them up and add, so what is that, 1? Negative half and negative half is negative 1, so that's negative 1x squared. And then now here's the hardest part. How do you add 1/24 plus 1/4 plus 1/24? Make a least common denominator. 1 plus 6 plus 1, that's 8/24, which is 1/3. So plus 1/3 x to the 4th, and those are the first 3 terms. Now, like I told you guys in class, if I was mean, I'd make you guys do 4 terms, because there's quite a bit of work additionally if you had to do that. Now, is that the only way to do the problem? Mr. Park, I don't like long multiplication. Well, then you got to think. Is there like an identity that I could use here? Because remember, in a previous homework problem, you had sine x, cosine x, and that was like half of the double angle identity. So maybe there's something with this. And there is. Okay, cosine squared x. Well, let's look at the double angle identity. Isn't that 2 cosine squared x minus 1? So if you solve for cosine squared x, add 1 to both sides. Divide both sides by 2. 1 plus cosine 2x all over 2 is equal to cosine squared x. Aha! So, another way to get the power series for cosine squared x then is to apply this identity. Just go 1 plus, do the power series for cosine 2x, and then divide everything by 2. So what's the power series for cosine box? Think of this as box. 1 minus box squared over 2 factorial plus box to the 4 over 4 factorial minus box to the 6 over, what the heck am I doing? Box to the 6 over 6 factorial plus dot dot dot. Actually, we didn't even have to go that far. Or did we? No, we didn't. And then look, all you have to do is add the 1 there and then divide by 2 and you're finished. So if you don't like long multiplication, then here's an alternative way of doing the problem. But it's up to you. But then you have to think about this, which poses a problem. Okay, number 4. A jar contains 3 red and 2 black marbles. Okay, this is number 4. So a jar contains 3 red and 2 black marbles. Bert and Ernie take turns drawing a marble. But this time it's with replacement. The first person to draw a black marble wins the game. If Bert goes first, what is the probability that Ernie wins? Well, how can Ernie win? Well, Bert could go first. Wait, I gotta read the problem again. Is Bert going first? Yes. So if Bert goes first, he could pull out the red marble, which is 3/5, put it back in. Then Ernie could pull out the black marble right now, 2/5. So that's one way Ernie could win. What's another way he could win? Well, Bert could go first, get the red. Ernie gets a red. Bert gets another red. and then Ernie gets the black on the fourth draw, 2/5. Okay, is there another way Ernie can win? Yes, Bert gets the red, Ernie gets the red. Bert gets the red, Ernie gets the red. Bert gets the red, and then Ernie pulls out the black ball on the sixth draw. Yeah, but the thing keeps on going forever. That's right, Moose Breath, because this is an infinite geometric series. And what is the common ratio? What do I need to multiply this by to get that, or to get that, and so forth? Oh no, right there. It would be this, 9/25. And the absolute value of that is less than 1, so I can use the formula. So the sum of an infinite geometric series is the first term, which is 6/25, all over 1 minus r, and I will leave the simplifying to you. So that, you want this problem to be on the test, because that's pretty darn easy. Except, since, just like the last test we had, or 2 tests ago, instead of Bert and Ernie, you might have snap, crackle, and pop. Or something. Okay, number 5. Oh, this is a beautiful problem. Write the first 6 terms of the power series expansion of 1 minus x squared to the -1 power. Now, -1 power means 1 over. And of course, this bar here means divide. So let's do some long division. This is going to be fun. 1 divided by 1 minus x squared. And I keep telling you guys, long division. If this number is a 1, it's easy to do long division. 1 goes into 1 how many times? 1. Multiply that times the divisor. Subtract. X plus x squared. Do the process all over. 1 goes into x how many times? X. Multiply that times the divisor. X minus x squared minus x cubed. Subtract. 2x squared plus x cubed. Do it all over again. 1 goes into this how many times? 2x squared. Multiply that times the divisor. 2x squared minus 2x cubed minus 2x to the 4th. Subtract. 3x cubed plus 2x to the 4th. 1 goes into that how many times? 3x cubed. Multiply that times the divisor. 3x cubed minus 3x to the 4th minus 3x to the 5th. Subtract. 5x to the 4th plus 3x to the 5th. 1 goes into that how many times? 5x to the 4th. And then, Mr. Park, I see a pattern. Hey, that's the coefficients of the Fibonacci numbers. Oh yeah, so then the next one is going to be 8x to the 5th. If that doesn't bring tears to your eyes, nothing will. Anyway, a lot of you guys got to practice your long division. You guys have, I don't know why you guys don't like long division. It's like a tool. You're going to BC Calculus next year. We do a lot of long division. Okay, number 6. 2 ways of doing this problem. Now, probably on the test, I'm going to tell you which way to do the problem because some of you, like if I don't tell you, it's like all over already. So n equal 1 to infinity. What do we got? 1 over 4n minus 3, 4n plus 1. Okay, now, the first way that I want you to do it is by just finding the limit of the sequence of partial sums. So, what you need to do is you need to write out at least 4 terms here. So, plug in 1. 1 over 1 times 5 is 5. Plug in 2. 5 times 9, 45. Plug in 3. 9 times 13. Whoa, what is that, 117? 1 over, now we're plugging in 4, 13 times 17. Is that 221? Now some of you might like actually labor because you have multiplication issues, yeah? All right, here we go. Look at the limit of the sequence of partial sums. So we're going to make a sequence of partial sums. So what is the sum of the first term? 1/5. Okay, now what is the sum of the first 2 terms? make a least common denominator, that's what, 10 over 45, which reduces to 2/9. What's the sum of the first three terms? Well, it would be this plus that, right? So if you make the least common denominator of 117, that would be, whoa, 27 over 117, which reduces to 3/13. I'm starting to see a pattern. Okay, and if you want to do one more, you can, but I think the pattern is pretty obvious over here. So what is the explicit formula for the sequence? N over 4n plus 1. They're both arithmetic, right? And what is the limit of the sequence? Well, if the degree of the bottom and the top are the same, you look at the coefficient, so 1/4. So the sum of this infinite series is 1/4, because that is the limit of the sequence of partial sums. Now, another way to do the problem is to decompose this into its partial fractions. Say what, girlfriend? Well, in the second quarter, when we studied rational functions, we learned how to decompose into its partial fractions. Okay, so let's kind of review how to do this. Well, what fractions, when added together, will give you this as the least common denominator? Well, it would be something over 4n minus 3 plus something over 4n plus 1. And then what you need to do is you need to figure out a and b. Now, this is not a difficult decomposition. This is a basic one. But then you go to BC, you have to be able to decompose the hard ones. Okay? Anyway, so first step, multiply both sides by the LCD. So you get 1 equals a times 4n plus 1 plus b times 4n minus 3. Now, when you get to this step, there's two things you can do. You can equate the coefficients. Well, I guess there's three things you can do. Or you can use the Heaviside method, or you can use a hybrid of the two. Now, when you have linear factors like this, Heaviside method is always the easiest. So, what is the Heaviside method? Well, you plug in numbers for n. Now, what would be a good number to plug in for n? Now, a lot of people would say 0 or 1, but don't be ridiculous. How about 3/4? Now, why would I plug in 3/4 for n? Because it will make that thing 0. So if I plug in 3/4 for n, you get 1 equals, plug in 3/4 there, 4a plus 0. A! I just figured out a is 1/4. Now, plug in another number for n. It really doesn't matter what number, but if you pick a good number, it's easy to solve. Like, how about negative 1/4, because it makes that 0. So if I plug in negative 1/4 for n, you get 1 equals 0 plus negative 4b. I just figured out b is negative 1/4. So that means this is 1/4, and that's negative 1/4. So this original problem then, instead of computing it in the form that it's in, why not put it in its decomposition? 1/4 over 4n minus 3 minus 1/4 over 4n plus 1. See, this is the same thing as that, except that we just decomposed it. They're equal to each other. Okay? Now, how do I compute this thing? Now, this is beautiful. So, are you ready? Plug in 1. If I plug in 1 for n, you get 1/4 over 1, which is 1/4, minus 1/4 over 5, which is 1/20. Okay, now plug in 2 for n. 1/4 over 5, that's 1 over 20, minus, we're plugging in 2 here, so 1/4 over 9, which is 1 over 36. Okay, now plug in 3 for n. 1 over 36 minus 1 over 52. Okay, now plug in 4 for n. 1 over 52 minus 1 over, what are we plugging in for? 68. And this thing goes on forever. Now, do you see it? You see the beauty of this thing? Look, this cancels that. Negative 1/20 and positive 1/20. That cancels that. That cancels that. That cancels that. So everything else cancels out. The only thing that's left is 1/4, that first term right there. So the sum of this infinite series is 1/4, but of course, it doesn't matter how you compute it, right? Whether you do it using plan A or plan B, you should get 1/4 as your answer. But don't worry, on the test I will tell you what technique to use. So do we have to know partial fractions? You don't have to know anything. I just can't believe we forgot partial fractions. Alrighty then. Find the interval of convergence for this series. Sigma n equal 1 to infinity of 2 sine x to the n. Yeah. Okay. Now I hope by this time you look at that and go, hey, you want geometric series. If not, then write out the first few terms, like plug in 1, 2 sine x, plug in 2, 4 sine squared x, plug in 3, 8 sine cubed x, dot, dot, dot. Hey, you want geometric series, right? Because what do I need to multiply this by to get that? 2 sine x. Multiply by another 2 sine x and you get that. Hey, that number in the parentheses, that's the common ratio. Duh, I think I told you that how many times already. So hopefully you would just recognize it right off the bat. Anytime you have like something to the nth power, it's geometric. The thing in the parentheses is the common ratio. Now, in order for a geometric series to converge, what has to happen? The absolute value of r has to be less than 1. This is how you determine your interval of convergence. So, you write that down on your paper, you get a couple points, now you got to solve it. When is the absolute value of 2 sine x less than 1? Well, how do we solve something like this? Well, there's lots of ways of doing it. Just figure it out, man. So, absolute value of gorilla is less than banana. You put gorilla in the middle there, and you put negative banana and banana there, right? Divide everything by 2. Negative half is less than sine x is less than a half. And notice that negative half and a half, these are numbers you're supposed to know, right? So, just think about it. Where is sine x between negative half and a half? Well, one way, how about think of the unit circle? Where is sine x equal to negative half and positive half? That would be at the pi over 6 family, right? Wouldn't that be here, like pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So where would sine x be between there? Wouldn't it be like there and there? Okay, now, how do you write that? Well, one way is to just write them all out, like dot, 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 and then how about negative pi over 6 to pi over 6, and then 5 pi over 6 to 7 pi over 6, and then 11 pi over 6 to 13 pi over 6, and then dot, dot, dot. So for those of you who don't know the k pi notation, then I guess this is the way you want to go. But if you want to be more concise, then you could just go, how about negative pi over 6 plus k pi, comma, pi over 6 plus k pi, where k is an element of the integers. Right? Because look, if k is 0, then you get this one. What if k is 1? Then you get that one. What if k is 2? Then you get that one. What if k is negative 1? Then you get the one over here. And so forth and so forth. I don't care how you write it. Pick one and go with it. Yeah, interval of convergence, that's definitely on the test. So all you have to do is, whatever the common ratio is, the absolute value of that is less than 1, and then you solve it. Which, of course, I guess that's going to be the toughest part for you guys. Okay, number 8. Compute the following series. Okay, now, I'm probably going to give you lots of hints on this test. So, it's going to make it easier. 2 to the n over n factorial. Okay, so the first thing you should do is write out the first 4 terms, or at least, okay? Plug in 1, 2 to the first over 1 factorial. 2 to the, plug in 2 to the second over 2 factorial. 2 to the third over 3 factorial. 2 to the 4 over 4 factorial, dot, dot, dot. Okay, so this is how your thinking should go. Is this a geometric series? No. Is it a power series? So that means you need to have your 5 power series memorized. If not, it could be significant pain. Well, is there a power series that has the consecutive numbers factorial in the denominator? Yeah, the e to the box one. E to the box is equal to 1 plus box squared over 2 factorial plus box cubed over 3 factorial plus box to the 4 over 4 factorial. So what number do I have to plug into the box to generate these numbers here? 2! So if I put 2 in the box like this, hey, that's that, except Mr. Park, this one. Look, this one is that, this one is that, this one is that. What do I do with this one? Move it to the other side. So this thing, do I have to write it out? I guess so. So this thing here is equal to e squared minus 1. So you got to figure out what number to plug in to the box, and then you might have to lomi it a little. E squared minus 1 is the answer. Beautiful. Okay, next one. B. What do we got here? Sigma n equal 1 to infinity of, no, it's 0 to infinity, fool. Some of you don't even look at that bottom number. I laugh at that. Cosine n pi over 2n plus 1. Okay, let's write out the first 4 terms. Plug in 0. Remember, you have to look at this number because I remember on the quiz, a lot of you got points taken out because you don't even look at the number. You just assume you're going to plug in 1. Okay, start by plugging in 0. If I plug in 0, you get cosine of 0, which is 1 over 1. Yeah! Now plug in 1. Cosine of pi is negative, so negative 1 over 3. Plug in 2. Positive 1 over 5. Negative 1 over 7, and so forth. Is this a geometric series? No. Is it a power series? Well, is there a power series that has the odd numbers in the denominator? Yeah, that's the tan inverse one, yeah? Okay, so let's write this. Tan inverse box is equal to box minus, box cubed over 3 plus box to the 5 over 5. Oh, I get it now, Mr. Park. We got to memorize the power series. Duh! Box to the 7 over 7 plus dot, dot, dot. Okay, so look at this. What number do I have to put in the box to generate these numbers here? 1! You can't get easier than that. Oh, so if I keep adding these numbers forever, you're going to get tan inverse 1, which is pi over 4. And this gives us a way of computing pi, right? Because look at this, right there. How would you solve for pi? Just multiply both sides by 4, right? So pi is equal to 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus dot, dot, dot. So this is one of the formulas we use, or infinite series that we use to compute pi. Of course, there's others, because this one doesn't converge very quickly. So we have other series, because we want it to converge more quickly so that if you want to estimate it, you don't have to use as many terms. All right, okay, that was fun. Okay, C. Ooh. Sigma n equal 1 to infinity 1 over 2n. Now, using your properties of sigma, when you have a constant, you can put it outside. So you have this, sigma n equal 1 to infinity of 1 over n. And you somebody. Well, if we don't recognize it, let's write it out. Plug in 1, plug in 2. Half plus 1/3 plus 1/4 plus dot, dot, dot. Hey, Mr. Park, this is the one you talked about in class, huh? This is the harmonic series. Harmonic series. And remember I proved to you in class that the harmonic series diverges to infinity? So this is an infinite sum. So what's half of an infinite sum? Another infinite sum. So this series diverges to infinity. Harmonic series. Anyway, and just to refresh your memory, the harmonic series is a special case of the P series. Remember this? Sigma n equal 1 to infinity of 1 over n to the P. This is just a case where P is 1. And remember, if P is less than or equal to 1, the series diverges. If P is greater than 1, the series converges. All right, next. Okay, D. A. This looks like the problem from the quiz. It's like exactly n equal negative 1 to infinity, 2 times 3/5 to the n. This is exactly the quiz. So I hopefully by now this is a geometric series because you got a number to the nth power. This is the common ratio. So why not? So if the common ratio is 3/5, the absolute value of that is less than 1, we can just go straight to the formula. Okay, the formula says the sum of an infinite geometric series is the first term. Now how do we get the first term? You have to plug in this number here. A lot of you on the quiz plugged in 1, but the first term you have to plug in -1. So the first term, if I plug in -1, is actually 10/3 all over 1 minus r, and I will leave the computation to you. You wish you get this problem on the test. Okay, E. Oh, I am seeing complex numbers which we need to use de Moivre's theorem then. N equals 1 to 100 in this case, of 1/2 plus √3 over 2i to the n. Okay, we did problems on the homework. It was on the quiz. First step. Change this into polar form. So how do you change from standard to polar form? Draw a picture. If I go 1/2 to the right and radical 3 over 2 up, right? Basically, it's like plotting the point 1/2 √3 over 2. How far from the origin am I? 1. What is that angle there? 60 degrees, or pi over 3. I think it's better to use radians. Okay, and there you go. Now just apply de Moivre's theorem. If I plug in 1, any complex number to the first power is itself. Now the key to doing this problem is you have to figure out how many consecutive ones are going to cancel out to 0. That's the key here. Okay, now plug in 2. Now how do you raise a complex number to the second power there? You go 1 to the second, which is 1, and then you multiply that angle times the power, 2 pi over 3. Okay, now what happens when you plug in 3? Well, applying de Moivre's theorem again, 1 to the third is 1. You multiply the angle times 3. Pi. Oh, I get it, Mr. Parker. I see a pattern now. Yeah, I think that's enough. Or if you did enough of these, you can kind of see what's happening already, right? So if you were to graph these vectors, now remember, complex numbers are vectors in the complex plane here. Okay, here's a circle of radius 1. That's terrible. Too bad we're going with it. How do you draw this vector? You make a vector 1 unit long, making an angle of pi over 3. Boom. What about this one? 1 unit long, making an angle of 2 pi over 3. Then this one, one unit long, pi. Oh, I see, Mr. Park. Every time you're adding 60 degrees to it. So the next one going to be here, the next one going to be there, and the next one going to be there. Oh, so every 6 cancels out to 0. Hey! Okay, so if I know every 6 cancels out to 0, and I have 100 terms, how do I figure out how much is left? Well, 100 divided by 6 is 16, remainder 4. So there's 4 left over. The first 4, right? Here's the first, second, third, and fourth. That's what's left over. And then, since these are pointing in opposite directions and they're equal length, they cancel out. So all that's left are these 2 right here. Now, what's this one? That's 1 kiss 2 pi over 3. And what's this one right there? That's 1 kiss pi. And then, of course, now we change it back into a plus bi form. Now, of course, remember, KISS is an abbreviation for cosine theta plus I sine theta. Cosine theta plus I sine theta. And then you just got to know your trig values. Negative half plus root 3 over 2I. And then negative 1 plus 0I. And then if we add the real terms together, what's negative half and negative 1? Negative 3 halves. And then if I add the imaginary with the imaginary, you get plus root 3 over 2I. Finished! That was fun. We need a bigger power than 100, Mr. Park. I paid good money to be in this class. Who are you talking to? F sigma n equals 1 to, no, it's 0. 0 to 180 cosine of n degrees. Okay, now if you're wondering what's going on, plug in numbers. So cosine 0 degrees plus cosine 1 degree plus cosine 2 degrees, all the way until you hit cosine of 180 degrees. Mr. Park, I don't know what cosine of 1 degree is or 2 degrees. What the heck am I going to do? Well, how about let's think a little bit. What if I draw the unit circle? Cosine of 0 degrees would be the x-coordinate of that point. Cosine of 1 degree would be the x-coordinate of that point, and 2 and 3. Now, I can't draw it that fine. And if I keep on going to 180, that's going to be the x-coordinate of that point. Oh! Wouldn't the x-coordinate of that point cancel that? Because that's 1 and that's negative 1. So cosine of that will cancel cosine of that because they're exactly the same length except negative. They're opposites of each other. And cosine of 1 degree will cancel out cosine of 179 degrees, right? Because the x-coordinate here and the x-coordinate there are simply opposites of each other. So 1 cancels cosine of 179. 2 cosine of 2 degrees cancels cosine of 178. So if you just keep canceling, there's only one thing left, cosine of 90. Well, what's cosine of 90? What? No, it's 0, fool. So the answer is 0. 1. I laugh at that. 0. All right. That was kind of fun. The complex number 1 was more fun. And then, what do we got here? Using the power series expansion of sine x, how many terms are needed to approximate sine of 0.5 so the magnitude of error is less than 10 to the negative 4? So the first thing you got to start out doing is write out the power series for sine x. So sine of, let's just put box is equal to box minus box cubed over 3 factorial plus box to the 5 over 5 factorial minus box to the 7 over 7 factorial. Now, we don't know how many terms we're going to need. Now, what do I need to put into the box? 0.5, because it says sine of 0.5, but 0.5 we know is a half. Okay, so now the question is, how many terms do I have to use so that the magnitude of error is less than 10 to the negative 4? Now, in order to use Leibniz's theorem, you have to make sure this is an alternating series, which it is, so I can use it. So what we're going to do is we're going to look for the first term that's less than 10 to the negative 4. That's 1 over 10,000. Here we go. 1/2 minus 1 over 8 times 6, 48. Is that less than 1 over 10,000? No, so you move to the next term. 1 over 32 times 120. Wow. 32 times 120 is 64, 32, 3840. Are you my mother? Or are you less than 1 over 10,000? No, so we keep moving to the next term. So 1 over 2 to the 7th is 128. 7 factorial is 5,040. Why don't we just write 504 there? So what do we got? 2, 3, 4, 0, 8, 0, 1, 0, 4, 0, 5, 2, 1, dig with a 0. So 1 over 645,120. Is that less than 1 over 10,000? You bet your baby it is. Did I even do that multiplication right? Feels like I did something wrong. But you know what? I'm too tired to figure it out. No, okay, I'll double check it. No, too bad. So once we find that's less than 1 over 10,000, just add everything before it. So the answer is 3 terms. Because the magnitude of error is going to be less than the first term that you didn't use. That's Leibniz's theorem. So the answer for this problem, 3. Okay, number 10. Here's the last one, baby. For what value of x is this series equal to 2? Okay, so you got a sigma n equal 1 to infinity of x to the 2n minus 1. What do I have to plug in for x so that you get exactly 2? Well, I don't know, Mr. I don't know what's going on. Well, how about write out the first 4 terms? Plug in 1, x to the first. Plug in 2, x to the third. Plug in 3, x to the fifth, x to the 7 plus ... equals 2. Now I see it, Monsieur Park. This is an infinite geometric series. Hey, what's the common ratio here? X squared. Oh, so the sum of an infinite geometric series is the first term all over 1 minus r. See, if you don't write it out, some of you just might not see it's a geometric series, so always write out the terms. And we want to know when will that equal 2. I think we can solve this equation. So, cross multiplying x equals 2 minus 2x squared. Make one side 0. 2x squared plus x minus 2 equals 0. That doesn't look factorable. So using the quadratic formula, x equals negative b plus or minus the square root of b squared, 1, plus 16, that's 17, all over 2a, which is 4. So 2 answers. Box that, that's the answer. You got to check, because remember, in order for an infinite geometric series to converge, the absolute value of r has to be less than 1. So in this problem, the absolute value of x squared got to be less than 1. Which means, since both sides are non-negative, x squared is less than 1. How do I solve this? Well, okay, why don't we try something? Square root both sides, because since both sides are non-negative. Square root both sides. What's the square root of x squared? Absolute value of x. What's the square root of 1? And what does this mean? X is between negative 1 and 1. So that is your interval of convergence. So you have to make sure your value of x is between negative 1 and 1. Are both of these between negative 1 and 1? Don't be ridiculous. The only one that is negative 1 plus root 17 over 4. Right? Because root 17 is 4 point something, right? Because if you put the minus 1, it's smaller than negative 1. Now, if you have problem solving, instead of square rooting both sides, maybe you guys should do this then. Make one side 0, factor x plus 1, x minus 1. Make a number line, negative 1 and 1. No, no, plus, minus, plus. Whatever, solve it. All right, hey, that's the last problem. Yay! And got some additional problems, but they look like the same as all the other problems. All right, that was fun. See you later.